Okay, with the usual stagger, next lecture. Models and transformations. Welcome to lecture 1.4. Okay, we're done with inverse functions for now. We're going to talk about proportional laws and power laws. We're going to talk about transforming functions and graphing those transformed functions. And we're going to talk about a little bit of scientific modeling and very, very basic parameter estimation. Okay? There you go. That's what the word proportional means. If the variable y is directly proportional to the variable x, sometimes written y proportional to x, then y is equal to cx for some constant of proportionality c. Okay? C is a constant. It has nothing to do with x or y. It might be tied to some other variables that are fixed. Okay? And I mentioned this before, don't worry too much about this, but this is what's true linearity, right? So we talk about linear functions being things that look like straight lines, but in some context, this is what you call linear, okay? It's got to be directly proportional. Okay, questions yet? Examples. Okay, we're going to talk about examples of physical laws led to by observations. So, direct proportionality. Hooke's law. Okay, for the force exerted by a spring. A nice, well-behaved spring. The force is proportional to x. X is the displacement from equilibrium. Okay? The amount of stretch or the amount of compression. Okay? So f at s is a function of x. You could write this. And notice I'm doing something I tried not to do before. Sometimes you let the variable and the function have the same name. Okay? So we're saying that the force exerted by the spring that's been compressed or stretched by a distance x, let's say its displacement from equilibrium is x, is given by this. Minus, because it's in the opposite direction, it's resisting what you're doing, k, the positive spring constant, okay, which tells you how stiff the spring is, and again, x, the displacement. Okay? Proportional. They're brother and sister, if you're not aware, amongst other things. Okay, you don't need to know this, obviously. Okay, some examples of proportional relationships. You'll see a lot of them. Let's see. Here we have Ohm's law. Here we have aspects of the ideal gas law. Here we have Hooke over there. Here we're talking about how the force between two charged particles is proportional to the size of, or sorry, the amount of charge in each one. The force of gravity is proportional to the masses of the two objects. Kinetic friction is proportional to the normal force. This is Henry's law for dissolving gases in liquids. When there's no turbulence, the drag on an object is proportional to its speed. You're going to see this a lot. At a given wavelength, the amount of light, let's not say that. The optical absorbance, which is defined in a curious way, is proportional to the concentration of stuff that's absorbing light and to the distance that the light has to go through. The rate of diffusion, for instance, across a membrane, is proportional to the difference in concentration of the solute on either side of the membrane, and it's proportional to the area that you're going across. And we'll talk about this a lot. Exponential growth is proportional. The rate of exponential growth is proportional to, for instance, the population size. Okay? Examples. That's it. Okay. Okay, so we talked about proportionality. Here's something else you can have. Power laws. For instance, the gravitational force between two masses, point masses, of fixed mass. Okay, the Earth and the Moon, they're not point masses, but they're symmetric enough that you can, use their center of gravity and it works. Okay? So what's the deal here? The magnitude of the force is proportional to the inverse square of the separating distance. This is familiar-ish. Okay, you got two masses, point masses. The masses don't change. They're a distance d apart. The force pulling them together because of gravity is proportional to the inverse square of the distance between them. Okay? And it's a power law because look at that. Okay, if you want to write this as a function, you'd write something like this. Okay, where c is a, in this case, positive constant. Okay? And if you know the law of universal gravitation, did I say that? The law of universal gravitation, this is g, the gravitational constant, times the mass of the first object times the mass of the second object. Okay? That's a power law. In particular, it's an inverse square law. Okay? You can say that the force, the magnitude of the force, is inversely proportional to the square of the separating distance. So I said this. Between two massive objects, the gravitational force is proportional to the reciprocal of the square of the distance between the objects. Okay? So what that means is, like, if you have two massive objects, for instance, okay, if you've not seen this before, if you've got two massive objects and you bring them half the distance together than they were before, then the force between them quadruples. Okay? And if you move them twice as far apart, then the force divides by 4. Okay? And another thing, after telling you that inverse and reciprocal are different things, I then went ahead and called that inverse square. Okay? Which is bad. Okay? Everyone calls that inverse square, but you should call it reciprocal square. Okay? Here's some more power laws. Okay, these three guys are all inverse square laws. Okay? The force between two charged objects, the gravitational force between two massive objects, and the light intensity a certain distance from the source, all scale as the inverse square of the distance. The rate of diffusion, which we just talked about, has to do with Fick's law. Scales as the inverse of the distance that you're diffusing across. The farther you have to diffuse, the slower that diffusion is. This is Boyle's law. P is proportional to 1 over V. The period of a mass spring system, I showed you the simple harmonic oscillator, has to do with the square root of the mass and the spring constant. One's in the numerator, one's in the denominator. Kinetic energy, 1/2 mv squared. So the exponent is 2. Drag force, we talked about no turbulence. If there is turbulence, the drag force is proportional to the square of the speed. And finally, this crazy thing, if you've got a hot black body, the radiation it releases is proportional to the 4th power of its temperature. Again, you don't need to know these, they're just examples. And speaking of just examples, I like animals. I hear some of you do too. Okay. This sort of thing, where you study how something scales with the size of an animal, for instance, is called allometry. Okay, so here we got 4 groups of animals. We've got the birds, the mammals, the lizards, and the amphibians. Obviously, nothing is going to look this nice. There's data points, and things have been fitted, let's say, well, to those data points. And what we've graphed here is the resting metabolic rate of the animal, how much oxygen it consumes per hour, and here you've got how big the animal is. Okay? And it's not proportional. The metabolism is not proportional to the size of the animal. Okay? It follows a power law. Look at that. Okay? The resting metabolic rate is proportional to a power of the body mass. Cool? Notice wonderfully and magically, all those exponents are close to 0.7. So there's something at work there. The constants of proportionality tell you how intense the metabolisms of these animals are. Okay? Birds have intense metabolisms. Mammals are less demanding. Amphibians are not very demanding at all. Okay? And again, we call this kind of relationship an allometric relationship. Okay? Because it's not proportional. Okay? Okay. Another bio example. Don't know how well you can see this. More power laws. Okay, so neurons are your nerve cells. Okay, they transmit signals through your body. The axon is the bit that does the transmitting. And the bigger the axon is, the faster the signals get transmitted. Okay? Conduction velocity, it should be speed, increases as the diameter of the axon increases. Okay? This is a log graph, don't worry about that. It makes power laws look like straight lines. Okay. And the interesting thing is that depending on the features of the axon, you might have proportionality, or you might have something that's more like a power law that's a square root function, like these guys, or you might have something in between. Okay? But again, you've got a power law. Good? Okay, I will start this.
Are we going to go back to this next class?
To this?
Yeah.
Yes.
Okay.
Just walk out now. Yeah. Okay, sometimes you've got simple functions and you want to transform them into more complicated functions to model what you care about. Okay? So for instance, x squared isn't much use in modeling the trajectory of a projectile, right? But if you flip this thing and stretch it like this and move it over and you get something like this, then there's some hope that that's going to model what you care about. Okay, so you want to transform things. Good? And we're going to talk about those kinds of transformations. Okay. Yeah, for 2 minutes I'm going to talk about this. Okay, the first kind of transformations are translations. Okay. You might want to translate a function if you want to, instead of starting the clock at, let's say, the year 1990, you want to now start the clock at the year 2000. Okay? You want to move the origin of time. You want to move the origin of position. You want to move your reference frame of velocity. Something like that you'd want to translate, as well as other things we're going to see. Okay? Or if you want to change the average level of something. So, those are the rules. You have those rules. They're in slides and they're in your handout, so you can look at those. And I'm going to very briefly talk about this for a second. And we'll come back to this next time. Given the graph of y equals f at x, want to graph y equals g at x, which is just f at x plus c, c a positive constant. Okay? So suppose you have the graph of f. Okay? For any value x, f has on it x f at x. Okay? What is g at x? G at x is f at x plus c. So g has on it the point x f at x plus c, which is just c up. Okay, so that distance is c. Okay? Just C units up. So you're going to do that for all the points on the graph, and you're just going to see, see, that the graph of G is just C units up from the graph of F. You just translate it C units up. Okay? That's it. We'll do the rest next time. Take care. Okay, translations. Those are the rules. Let's see how they work. So we talked about how you might want to translate a function or a graph to move the origin of velocity or time or position or something, or to move the mean value of something. Okay, here's an example. This is the same as last time. Given the graph of f, you want to graph G, where G is f plus c. C a positive constant. Okay? And we said that, suppose we have a graph for f, at any value of x, the y-coordinate on this graph is f at x, and the point on the graph at x, on the graph of G, is at f at x plus c. So here, okay? C units up. So if you do that for every point on the graph of f, then you see that the graph of G is just f shifted up c units. Is that cool? Any questions about that? Okay. And that's what the first one says. Okay. Second example. Again, given the graph of f, you want to graph G, where G at x is f at x minus c, all in brackets, c a positive constant. Okay? Same deal, let's look at f. Okay? At any value of x, the y value for G is going to be the y value that f took c units ago. So, c units ago is here. And the value that f took is this. So G takes that value here. Does that make sense? Again, so you look at a particular value of x, you see that at that x, G will take the value that f took c units ago. C units ago is here. This is where f was, and G is there now. Okay? And so if you do that for all the points, you see that you shifted right c units. And, yes. Can we pretend that looks right? Okay? So the graph of G is the graph of f shifted right by c units. Okay? There's a subtraction here, but it's to the right. Okay, and in high school, I imagine that caused some headaches. Does that make sense? Okay. So this graph is kind of lagging, okay?
It's lagging to the right.
Yeah, maybe, okay, forget I said that then. Yes, it is lagging, but yeah. Okay, basically it takes the same value but later. Yeah? Yeah, I say lagging, but you might think, well, lagging probably means it's behind this way, but no, it means it's that way. Okay, again, so if you see x minus 2, then it's shifted to the right 2 units. Good? Okay, for instance, that's just going to keep growing, isn't it? You want to graph? Wow. Okay, you want to graph this, the square root of x plus 2 minus 1. Okay, so you can... You all know how to fix that? Good IT.
Try turning it off and on again.
We'll see, and then I'll fiddle with the volume. Okay, any questions so far? Okay. All right, so let's... Here's the deal, I'm going to shout for a while, okay? And if I'm not shouting loud enough, again, tell me. Okay, here we go. We want to graph y equals square root of x plus 2 minus 1. So let's start with the graph of the square root of x, which looks like that. Okay, and you can put some sample points on there and then draw a curve through them. That makes sense. Okay, so what do I have to do to this graph to get the graph of this?
Move it 2 units to the left.
Say again?
Move it 2 units to the left.
Yes, and?
One down 1.
Excellent, good. 2 units left, again, plus means left, and down 1 unit. Perfect. Two units left, down 1 unit. Two units left, down 1 unit. And that's the graph you want. Okay? And if you want, you can find the domain and range of that and see that it agrees with what you thought it should be. Okay? Okay. All right. Questions? Scalings now. For instance, if you want to change the size of something, or the duration of something, or the period of something, or the amplitude of something, or the units of something, then you might apply a scaling. Those are the rules. You can think through those the same way you thought through this kind of translation stuff, okay? So, if you multiply by a factor of, if you multiply by c, and c is greater than 1, then you stretch vertically by c. This is saying essentially the opposite, so you compress if you divide by c. And here, again, notice that the horizontal rules are the opposite of the vertical rules. Okay? Does anyone have any questions about this? You want me to show any of this? Who wants me to show one of these? Right, good. Okay, I'll show the bad ones. I'll show that one. Or maybe I'll show that one. Okay. This one is fairly easy to see, right? So you're multiplying the output values, right? So all the functional values by c. So the whole thing stretches by c, okay? By a factor of c, okay? So let's do that one. Okay, again, given the graph of f, we want to graph c greater than 1. Okay? Okay. Let's draw something manageable, like this. Okay, let's say that's the graph of f. Let's say it's the graph of y equals f at x. Okay, and think exactly the same way as before. You want to know what value this guy takes at any x. Okay. That's a bad choice of x. Okay? Let's call this g. Okay. At x, g will take the value that f takes at c times x. So c times x, some multiple of x, say over here. Okay? So c times further out that way. So that's the value it took there. That's f at cx. And so that's the value that g takes here. Good? So you'll notice it's become compressed. And similarly for all other points here. Okay? And so this is the graph of f, and this is the graph of g. Does that make sense? Yeah.
So just to clarify, you're compressing the x value, right?
You're compressing this way. Yes? Is that what you mean?
Yeah.
You're compressing like that. Okay.
Can you show like numbers?
Yeah. Yeah, I'll show you something with numbers. Does that make sense in principle? Okay, just don't get the two confused, okay? Don't get the stretches and the compressions mixed up, okay? And again, they're different for y and x. Questions about this? Okay. Again, those are the rules. Learn those rules. And ask me anything if you want to. Let's do another example here. By the way, EG and EX mean the same thing. Okay, suppose we have a sinusoid. Okay, 0 pi, 2 pi, 0 minus pi, minus 2 pi. Who knows what this is the graph of? Sine, yeah? Officially you don't know that yet? I'm not shouting, am I? Okay. And suppose you want to draw the graph of sine 2x. So what do? Do you compress or do you stretch? Compress. Vertically or horizontally? Horizontally. Good. Exactly. So you get and this goes on forever. So what happens? Is that too much? No. Here, let's do it this way. What a beautiful graph, okay? The amplitude doesn't change, but the whole thing gets compressed, okay? So the period here was what? 2 pi. The period here is pi. Perfect. Good? We compressed it, the period got divided by 2. Okay?
So the operations affecting the x values.
Yeah.
Good.
Yeah, stuff in here affects you horizontally. Okay, does that make sense? Okay. Again, learn those rules, practice those rules, use graphing calculators or online tools to practice those things. And if you got any questions, just ask me. Reflections. So you'd need this if you wanted to reverse the direction of motion or flip the direction of force or something like that. And again, there you go. Those are the rules, okay? Those are even easier to think about. There's nothing too weird going on. You can think about those in roughly the same way. And if you have any questions, let me know. Any questions right now? So the graph of y equals minus f at x, you just reflect the graph of y equals f at x across the x-axis. And the graph of y equals f at minus x, you reflect across the y-axis. Okay. And if you like, think about what that means in terms of even and odd functions, right? Because when we talk about even and odd functions, we define them in terms of minus f at x and f at minus x and this. So you can think about what does that mean in terms of this and the graphs of even and odd functions. Okay? Here we go. Okay, don't worry too much about the specifics of this example. We have a positive point charge at the origin. So at the origin, we have a positive charge plus q. The resulting electric field at any other point on the x-axis is given by this, and its graph is that. Okay? So the electric field from a positive charge goes outward. Okay? So the electric field here is positive, and the electric field here is negative. You don't need to know all this, it's for the sake of application. Okay, so given the graph of the electric field, graph the electric field as a function of position if the point charge at the origin, instead of being plus q, is minus 4q. What do we do? Or just know this fact, okay? So the electric field scales proportionally with the charge that's producing it, and the electric field reverses if you've got an opposite charge. Yeah, go ahead. Say it one more time. You reflect, so this way, x-axis good, and then you stretch, yeah? Okay, that's fine. Yep, good. Okay. And it turns out they're reflecting, anyway, it doesn't matter, we won't say that. Okay, so if we change it to minus 4q, then the field reverses, okay, because negative charges are field sinks. Okay, so the field reverses in direction, and its strength is amplified fourfold. Okay, and you can see that kind of thing by looking at this, right? There's a q there. If that gets replaced by minus 4q, you can see that you're going to get a minus sign, and you're going to get a multiple of 4. Okay. So there you go. Like you said, flip it across the x-axis because you have that minus 4 in front. Because you have that minus in front, sorry, and because you have that 4 in front, stretch it vertically by a factor of 4. Okay? And that's what this trick is. Okay? This guy flipped and stretched by a factor of 4. Any questions about this? Okay, we're good? Again, watch out for the differences between x and y transformations. Notice that when you do a transformation, x transformations change the domain, and y transformations change the range. And that's it. So let's talk about combining transformations for a second. Is anything unclear right now? Okay. So, you probably aren't going to get just one of these transformations happening. You're going to get a bunch happening at once. And you might be given an equation where a bunch are applied at once, and then you have to graph. Okay? So one way you can do it is you can just build up, right? So you can apply one transformation at a time until you build up to the equation you were given. Okay? Or, and this is what I was taught to do, okay, so suppose you have the graph of f, and you're asked to graph g, and they're related. And you're able to write g like this, okay? If you're able to do that, then you can just look at this and figure out what you need to do. So what you do is first, stretch and flip according to what A and K tell you to do. Then shift or translate according
The shape.
to what P and Q tell you to do. Okay? There's other orders possible, but if you write it in this form, do it in this order. Do the stretches and the flips first according to A and K, then do the shifts according to P and Q. Does that make sense? Okay? So again, if you're asked to graph G and it's related to a function f in this kind of way, or you can rewrite it in this kind of way, then this will tell you what to do. Okay? So for instance, if you're given an equation like something like that, what do you do to get it into that form? It's 3 words.
Factor.
Complete the square. Did somebody say complete the square? You can graph it by factoring, but to get into this form, you complete the square. Okay? And you'll get something that looks like something squared plus something like that. Okay? And if this had if this had like a 3 in front, you get 3 out here, something like that. Okay? And this is in vertex form. And it tells you where the vertex is, and it's in that form. And you can just take the parabola, y equals x squared, and you can stretch it and shift it and everything to get it to the graph of the equation that you were given. Does that make sense? If you crave examples, let me know you crave examples. Although I might have to do those in tutorial or something. Okay? Okay. We talked about another transformation in tutorial, which was taking the absolute value of a function. We'll talk about transforming sine curves next week, I believe. So let me do something I like from biochemistry. Any questions right now? Okay. Okay. Example. Oxygen dissociation. No, you don't need to know this. Curve of myoglobin. You learn about this in physiology, animal physiology, biochem, if you take those things, obviously. Myoglobin is a protein that picks up oxygen, okay? It's in muscle, for instance. And
We did it. I did it in physiology.
its binding characteristics can be described like this. Okay? This is called the fractional saturation. It's the number of binding sites occupied by oxygen. Okay? This thing binds oxygen. This tells you how saturated myoglobin is with oxygen. This is the oxygen level, okay? Or the oxygen partial pressure, or the oxygen tension in solution. And this, let's say, is a positive parameter. It's a pressure. Let's not say what it does. If you ask me, I'll let you know. Okay? Good so far? So that's a constant. That's the independent variable, and that's the dependent variable. Okay? Now, who knows what this is going to look like roughly? That sounds good, yeah. Yeah. Okay, so it's like a parabola, hyperbola, sine, what sort of thing?
It kind of looks like this.
Hyperbola would be good, but why? Okay, you can rewrite this thing. Again, like I said, if you can rewrite stuff like that, hey, you're good. Okay, that's the same as that.
Yeah, that's yeah, see, it's like really stretched out. I must miss it.
Okay, so you can rewrite that as that. Okay? Okay. So this is what transform. This is essentially the graph of y equals 1 over p transform, right? Which would look something like this. That's y equals 1 over p. Good? Yes?
Can you just go over
How I did this? Magic? Honestly, okay, what I did was I knew that, okay, there's a p up here. I wanted to have, again, this is with practice, or you do probably polynomial long division would work, that kind of thing. Anyway, so what I knew was that I wanted a constant up here, so I knew that I had to take out as many p's as I have up here. And to do that, I use one of these, okay? There's one p here, there's one p here. So I just take that out somehow, and that leaves minus k. That's what went through my head, but you can do it in other ways. Okay? There's other ways of doing this. You could just write this equals a over this plus b, and then solve for a and b, do it that way. You could probably do long division and do it that way. Yeah? Again, just an example, I'm not really... Okay, yeah. Good? Alright, that's the graph of y equals 1 over p, yeah? Which points do I care about? Okay, at k, it equals 1 over k. At 2k, I think, it's at 1 over 2k. Okay. Now what do I need to do to this what do I need to do to that to get the graph of this? What do I do first, stretches or shifts?
Stretches.
Good, stretches and flips first, okay? All right, I'm going to flip vertically, and I'm going to stretch vertically by a factor of k. Okay? So, again, I'm going to flip vertically, and I'm going to stretch vertically by a factor of k. So the flip gives me this. And the stretch by a factor of k brings this guy down to minus 1 and brings this guy down to minus 1/2. That's not very good, is it? Conceal, don't feel.
Conceal, don't feel.
Good? Okay, does that make sense? Flip and stretch by a factor of k. Do you like my inequality shirt?
Yeah,
Yeah.
I noticed. I really like that.
Okay.
That's the Elsa shirt.
Yeah, I wear the inequality shirt on not inequality day, and I wear the Elsa shirt when I don't say the Elsa thing. Where is P over 2? Okay? Okay. Now what do? Now I shift, yeah? So I shift left by P and up 1. So in biochem, they're going to tell you this is hyperbolic, but no one's going to say why or how you get anything. So here you had flip and stretch vertically, and now you're going to have shift. Okay, shift left by P and shift up 1. Sorry, shift left by, did I say P the whole time? Shift left by K and up 1. Okay. So, shift this guy left by K, this point goes over here. Shift up 1, it ends up here. This guy gets to K, and then up to plus 1/2. This asymptote gets shifted up by 1. Okay. And so we're going to have something that looks like this. Pretend that went through. Okay? And that other branch is going to do something we don't care about. Okay? Does that make sense? And I'm sorry it says shift by P, okay? You shift it left by K. K is the constant. Are we good here? Okay, and this bit, this stuff doesn't matter. This bit, that's the curve. That's the dissociation curve of myoglobin. Okay? The higher the level of oxygen, the more oxygen gets bound. And K is the partial pressure at which half of all binding sites are occupied. So everything makes sense. Any questions? And that asymptote gets shifted up by 1. So it winds up here, somewhere. Okay? And the vertical asymptote gets moved left, K. This bit I didn't draw last time. Okay? And so the whole thing looks sort of like this. Okay? And the other branch winds up here somewhere. And it just looks like this guy turned around that point. Okay? Does that make sense? Okay. What I did last time was I just focused on this bit because this is the only bit that's physically meaningful. Okay? But this is math and you care about the whole graph, so I just wanted to show you that everything else makes sense. Okay? Yeah.
In that second graph, you have y equals negative k over p.
I want to say it's right, yeah?
Yeah. So you could rewrite that as y equals negative k times 1 over p, right?
Negative K times 1 over P. Yeah, that's, yeah.
So for the rules, didn't you say that if it was like c times x, it would be compressed instead of stretched?
Yes, but the X here is the P. Yes?
Right. So if that's
You're moving the K downstairs, is that what you're doing?
yeah.
So I'm saying if you have Y equals minus K like this,
Yeah.
that's exactly what we talked about, right? We had this guy, you multiply the whole thing by minus K, so that means a vertical flip and a vertical stretch by K. What you might be saying is that you could rewrite this as this.
No.
No, you don't mean that? Okay, fine.
Never mind.
It's all good? This is something you could think about. Okay, we went from Y equals 1 minus P to Y equals minus K over P. And I said, because you're multiplying the whole function by minus K, that's a vertical flip and a vertical scaling by K. Okay? Or a vertical stretch by K. You could also write this as this, amongst other things. Okay? That's exactly the same as that. Okay? But what does this suggest? This suggests that you stretch horizontally by K and flip horizontally. Okay? They're both right. Both will give you the right answer. Okay? So it's possible to have transformations that look different in equations but actually look the same graphically. Okay? They have the same effect but they look different in the equation. Yeah?
Why is PX?
What is PX? Because it was partial pressure and I wanted to be a good boy and use the right yeah. Good? Yes. You can think of it as that. Okay? So sometimes different-ish transformations are equivalent. Okay? And the reason here that a horizontal flip and a vertical flip do the same thing is because this function is odd. Any questions? I can get past this lecture if it kills me. Okay, and incidentally, if you do biochem, there's a Michaelis-Menten curve or equation in kinetics, and that has a similar kind of shape, and you can find it in a similar kind of way, okay? Oh, you don't. Question? Let's try this again. Okay, scientific modeling. This is going to be very, very basic parameter estimation. Okay, suppose the diameter of a tree trunk may be accurately modeled as a function of time by that equation there, or that function there, where A and B are constants. In 1990, the diameter was measured to be 40 centimeters. This is on, right?
Yeah.
Great. Exactly 20 years later, the diameter measured 60 centimeters. We take the time of our first measurement as t equals 0, determine the values of A and B, and estimate the year in which the tree began to grow. All right, that example. All right, so what are we told? We're told that d at 0 is equal to what, 40? And d at 20, and we'll deal with units afterwards, d at 20 is equal to 60, yeah? Okay. All right, so let's plug into the equation we were given then. So 40 is equal to a times the square root of 0 plus b, and 60 is equal to a times the square root of 20 plus b. I hope. Good? All right, can we solve this? Better hope so, right? Okay, what do you do? Someone give me some idea and I'll do whatever you tell me to. Yeah, right at the back, yeah.
You can isolate A.
That'll go fine. Yep. And up here? Yeah, that's fine. Okay, so good, you can do that. What I did was I sort of divided the one equation by the other, which gives you the same result. So yeah, you could isolate A. Okay? You could plug that into this guy. Okay? Multiply both sides by root b. Okay, then what would you do? Simplify life for a second. Sorry, 3 and 2. Okay, what'd you say? Square, someone said? Okay, good. Square everything. Okay? Okay, we got 9b minus 4b is 5b. 80 over here. What's that, 16? 80 divided by 5 is 16. Okay? And A, yes?
What happened in the third step?
What's the third step here?
That one.
I squared everything.
Oh, okay.
Square, 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 square. Good? Okay, and then I plug into that guy there. I plug B into that. 40 divided by 4 is 10. Okay? All right. This was in years, yeah? So what units does B have to have? Somebody shout something. Okay, when you add two things, they better have the same units, okay? So B has to be in units of years as well. Okay, what units does A have to have? You want to get centimeters out. You've got years in here, so you've got the square root of years. Okay, so you want to cancel out the square root of years and give centimeters. .5 up here. Okay? Are we okay? And you can check that those satisfy both of these guys, okay? Sometimes it's a good idea to check things, especially when you're squaring and doing recordings. Are we okay there? Yes, ma'am.
Do you also write centimeters squared per year?
Can you write centimeters squared per year? If you do that, look, because the thing in here, this is going to be in years. This whole thing is going to be in square root years. Does that, okay. Good? All right, and we're asked, when did the tree start growing? And that's really pushing the validity of this model, but let's pretend it's possible. What would I do to see when this thing started growing? When something starts growing, its diameter is 0, right? So solve for T0 in the diameter being 0. Okay, so find out when the diameter was 0, and you can say that that's when the tree started growing. So So 0 equals a, which is 10, square root of t plus b, which is 16. Can someone tell me the answer right away? Minus 16? Yeah? If this whole thing's going to be 0, you can divide both sides by 10, so that's going to be 0. The square root is 0 if and only if the stuff inside is 0. So t plus 16 has to be 0, so t has to be minus 16. Okay? So the tree started growing 16 years before 1990. 74. Therefore, started growing. Okay? Alright, if you want another kind of example like that, I think your assignment is almost exclusively examples like that. If you want something else, I can provide that for you. Okay, notice that in real life, usually you're not just interpolating, you're not just given 2 points, you fit exactly to those points, right? You fit using least squares and that kind of thing, and we'll talk about that later. Given 2 points, you can fit quite a lot of things to it, right? If you're given 2 points, you can fit there, you can fit that, you can fit a sign if you really wanted to, right? Okay, so you better know what you're doing, okay? So you want to actually fit something that makes sense, okay? And if you have more data points, that helps you. And if you have an understanding of what's going on, that also helps you, okay? And that's all I'll say about that. Any questions right now? Yes, ma'am? One more time. Yes. What was the point or why? Why did, okay, first of all, because things have to have units, so that's why I did it. And why is it years is because in here, the 20 was in years. And when you add two quantities, they have to have the same units. So B has to be in years. What about the A? Okay, so this is in years. You're going to take the square root, you're going to get square root years. The only way to get centimeters out here is for this guy to be in centimeters over square root years. And then the square roots cancel each other, okay? Good? All right.